All right, today's lecture is going to wrap up Chapter 10, which is on gases. All right, so today we're going to focus about real versus ideal. When we use the ideal gas law, or any gas law, we assume that all gases are exactly the same. We treat them as all being, they react, or I should say react, but they are treated in a container all to be the same. The only difference is their mass per particle would be different. Okay, when we look at ideal gas laws, the reason why we use it is because it's a very simplistic equation. It's easy to calculate. In real life, the calculations are much more difficult. So the benefit of the ideal gas law is it gives us a quick estimated value using a very simplistic equation. Some gases follow the ideal gas law better than others. And what this lecture is going to look at is what to look at for gases to determine if that gas law will follow the ideal gas law better or if it will not follow it much at all. To understand that, we saw this postulates in the last lecture. It's on the top of one of the, like the third or fourth page from the end. These are the assumptions we make about the ideal gas law. The first is the gases are in constant random motion. So the molecules move throughout the container until they collide off of something. Okay? If you were to draw a container of a gas like I have up here, where you have all the A's kind of in one tight corner. Some of you did this with the quiz, where you put all the A's and B molecules in separate places all tight together. That would not be a good picture, and you might be docked a point for that for gases. The molecules, because they are in random motion and moving all throughout, whenever you draw a picture of a gas, you want to make sure that it's homogeneous. So you want to make sure the molecules are all spread throughout and that the volume of the gas equally keeps the concentration the same throughout. Okay? The collisions between the gas molecules are elastic, which means they bounce off of each other. And because of that, there's no loss of energy. Just like two billiard balls, when they strike each other, okay, if they were to hit each other, they might bounce off each other and travel on different paths. When they bounce off each other, that's called an elastic collision. But there is no loss of energy with an elastic collision. Therefore, the molecules don't slow down constantly as the molecules collide. And if they did, then the temperature of the gas would constantly drop. So energy during the collisions is conserved. The volume of the container is, the volume that the gas particles take up in the container is negligible. So down here I've drawn a picture. Picture 1 shows a gas equally spread throughout in a container number 1. What this is saying is in the second container, if I packed all of the particles together as tightly as I could pack them, in essence making them a solid, you can see down here in the red corner, I packed all those same number of molecules into a very tight corner space. The volume of the container, let's say, is 1 liter. Well, the volume of the container really for the gas is the amount of space that the gas can travel throughout. Technically, the true volume would be the 1 liter minus the space that the particles take up. Because that is the true amount of space that the molecules, the particles can travel throughout. So, gases that are small gases follow this assumption better because they take up less room because they're smaller. So look at the molar mass of a gas. The smaller the molar mass, the smaller the gas is physically, and therefore it takes up less room. And therefore the volume that the gas travels throughout is very close to the actual true volume of the container. In actuality, we have to subtract off the volume of space taken up by the particles, which can be very difficult to do. So smaller gases follow the ideal gas law better than bigger gases. So the bigger a gas becomes, the less ideal it is. The attractive forces, we call that the intermolecular forces, are negligible. So we assume that the molecules, that there is no IMF attractions. Which gases follow this postulate the best? Gases that are nonpolar. Nonpolar gases or noble gases follow this postulate this assumption the best because nonpolar gases have the lowest IMFs. So the smaller a gas is, and if it's nonpolar, those gases should follow the ideal gas law. Therefore, the value that I get from the ideal gas law should be very comparable to the actual value in real life. Okay? Small gases that are nonpolar. So if it's nonpolar, we're looking at gases that are symmetric. And if you remember back to IMFs and intermolecular forces, symmetric gases are those that have all the same atoms coming off of it, and it has no lone pairs of electrons. So draw the Lewis structure. If a gas is symmetric, it's nonpolar and should follow the ideal gas law very, very well. The other two postulates, 5 and 6, we talked about in the last lecture with temperature kinetic energy, which I'll talk about briefly here in a second as well. One other thing that I do want to talk about here is what's called the Maxwell-Boltzmann. This is called the Maxwell-Boltzmann distribution graph. If I were to have a balloon of hydrogen gas, let's say helium gas, okay? If I were to take every single gas molecule and figure out what its velocity is and plot it on the graph, this is what I would see. Some molecules are moving very slowly, some are moving very fast, okay? And we get this beautiful bell-shaped curve. Most of the molecules are traveling, in essence, at the average point or the midpoint. Okay, so the Maxwell-Boltzmann distribution graph is looking at every single molecule, plotting it with its velocity. So we can see on the x-axis is speed, its velocity, and how many molecules have that velocity. And when we do that, we get this beautiful bell-shaped curve. It's not perfectly, because you notice on the very far right that it doesn't go down to 0 like the initial start of the graph is. So it does lag off. In essence, it's almost like a limit. It'll never reach the 0 point again. So because of that, it's not a perfect bell-shaped curve. But we can still treat that the apex of this line, the center, would be the average velocity. So what we see here is the blue line is looking at a gas that's at 0 degrees, and the red one is at 100 degrees. So we're looking at the same gas, but different temperatures. So if I take this helium balloon and heat it up, what do we know is true? At a higher temperature, the molecules are moving faster on average, and that's what we see. You'll notice that the midpoint of the graph is shifted to the right with the red line. Okay, the peak of the bell, the average velocity is further to the right because at a higher temperature, the molecules will have a higher average velocity. So at a higher temperature, the Maxwell-Boltzmann distribution graph, 3 changes happen to its overall shape. First of all, at the higher temperature, going from blue to red, at the higher temperature, you'll notice that the peak, okay, is not as high. Okay, the peak of the red line is much further, it doesn't go up vertically as high. The graph is broader. It's got a broader shape. It's wider. Okay? While we get to higher temperatures, all the velocities tend to increase more, not just the average velocity. There's overall more of the molecules are gaining, and therefore the width of the graph increases. And most importantly, the peak itself is shifted to the right. And that's because the peak, again, is the average velocity. So because it's shifted to the right, the molecules have a higher rate of speed on average. So this is called the Maxwell-Boltzmann distribution graph. It's looking at what if we were to plot all the molecules of a container of gas, what would it look like? It would look like, in essence, a bell-shaped curve. You might see a graph here where it's the same gas but at different temperatures. The higher temperature will be shifted further to the right. Another application of this is looking at 2 different gases but at the same temperature. Again, from the last lecture, if we have 2 gases at the same temperature, temperature of a gas is directly correlated to the average kinetic energy of the gas. So if you have 2 gases at the same temperature, they have the same kinetic energy. Are the molecules moving at the same rate of speed? Well, the equation for kinetic energy is 1/2 mass velocity squared, 1/2 mass velocity squared. if the mass of object A is less than the mass of gas B, the velocity of gas A has to be higher than the velocity of gas B so that the kinetic energies of both of them are the same. So the lighter the gas, the faster its average velocity. So if I've got two gases at the same temperature, they will produce two different bell-shaped curves, even though their kinetic energies are the same. Okay? So let's say the yellow line and the blue line, gas 1 and gas 2, are two different gases. Let's say one of the gases is CO2 and one of the other gases is helium. Which line is which? The average velocity of the yellow graph is at about a speed of 500 meters per second. The blue graph, its average rate of speed is about 1,100 meters per second. The blue graph has its average velocities being much higher than the yellow graph. Who is that going to be? Is helium going to be having a higher velocity, or is carbon dioxide? Helium is graph 2, carbon dioxide is graph 1. Since carbon dioxide has got a higher mass, its velocity, its particles are going to be moving slower on average. So its peak, its average velocity, will be further left because it's not moving as fast as the lighter gas is. So again, these might be multiple choice questions you might, or you'll have two different gases or three different gases, and the gas that's furthest left is the heaviest, and the furthest right is the lightest, because the lighter a gas is, the faster it has to be traveling in order for their kinetic energies to be the same. But again, this is only true if the gases are at the same temperatures. Okay? So some types of concepts. On the quiz for this week, you will see some multiple choice questions utilizing these different graphs. The last thing for this unit, and then we are done, is looking at when I calculate the value of the real gas. When we look at real life scenarios, what is the value? Let's say we're looking at volume. If I use the ideal gas law, I get a volume from the ideal gas law. If I look at the real gas situation under the same conditions, what volume does the gas attain? That'd be the real life example. So the question becomes is how comparable is the ideal gas value compared to the real value? This table is looking at deviations. Deviations mean when we have a higher deviation, that means that the real gas, that gas does not follow the ideal gas law well. So the value we get from the ideal gas law is not very comparable. The value in real life is not even close to what the ideal gas law gives us. So the bigger the deviation, that tells me that gas does not follow it as well. Now in this graph, we are actually looking at the oxygen and carbon dioxide. This graph is specifically looking at conditions of pressure and temperature. So looking at the deviations, as I look at oxygen, as I go from 1 atmosphere down to 10, down to 40, as I go down the graph, the pressure is increasing. What's happening to my deviations? They're getting bigger and bigger, which means at higher pressures, there's more deviation, which means when I run experiments under high pressures, I am not going to get a value that's very close to the ideal gas law. Temperature, when I go across, as I decrease the temperature, I'm going from 50 to 0 to negative 50. As I go across the graph, as the temperatures are getting colder, the deviations are getting larger. So at lower temperatures, there is more deviations. So the conditions that are the worst possible conditions would be low temperatures and high pressures. These are the two conditions that are the worst when it comes to gases. So we would want to run experiments at very high temperatures and very low pressures. In doing so, the molecules are as far apart as possible, which minimizes the intermolecular forces. And also because they're spread so far throughout, there's a much greater volume, the molecules aren't taking up as much space. So the volume approximation is also very good. So we can also make a gas that doesn't follow the ideal gas law very well. We can improve its ability to follow it by controlling the conditions. Now, at very low temperatures and high pressures, the gas is getting very close to the liquid state. We can see that here with carbon dioxide. So the colder a gas gets and the more pressure on the gas, we're getting the gas closer and closer to liquid state, which would make sense. If it's becoming closer to a liquid, it's not going to follow a gas law very well. Okay, so again, the two assumptions that are critical. We assume that the gas particles take up no space. So the smaller a gas is, the better it is. The gas particles are not attracted to one another. We are looking for gases that are like noble gases, which don't have very much IMFs, or we're looking at nonpolar gases. Nonpolar gases have low IMFs, they don't attract to each other very well, and they're going to follow the ideal gas law better. So gases that meet these criteria will be better suited at following the ideal gas law. Therefore, the value we get from it is very close to the approximation. All right, so here down below are two examples of conceptual questions that could be multiple choice or on an FRQ where you're asked to explain. I would like you to pause the lecture now and try to provide an answer to each of these questions. When you're done, start the lecture back up again, and I will show you the answers. All right, in the first problem, the first thing that I did is that I drew the Lewis structure. I would strongly recommend in questions like this that you draw the Lewis structures, mainly to look at letter B here, the attractive forces. Methane, CH4, is perfectly symmetric. It's a nonpolar gas. Oxygen and hydrogen are bonded to themselves, which means it's also symmetric and they're nonpolar. Since they're all nonpolar, we are really not looking at concept B. Because they are all nonpolar, they tend to have very low IMFs with each other. So now it comes down to the size of volume. The smaller of the gases will follow the ideal gas law better because it doesn't take up as much room. Therefore, when I squish all the gas molecules together, one gas might take up this much room and another gas might take up this much room. So the more room it takes up, the worse the approximation is in the saying that the gases take up no space in the container. So hydrogen would follow the gas law the best. The values we get in the ideal gas law would be much closer to real life because hydrogen is nonpolar, it has very low IMFs, and it is the smallest gas of the three, and therefore it takes up the least amount of room, and therefore will follow the ideal gas law the best. Number two, when you draw the Lewis structures, sulfur dioxide, because sulfur has 6 electrons, the Lewis structure of sulfur dioxide looks like this, where that you have a double bond to one oxygen and a single bond to the other. Some of you might have drawn the Lewis structure where it has double bonds to each, which is okay. This one does not follow the octet rule. This one does. But either way, even if you didn't draw it the way that I have it, in either case, both of the sulfur dioxide molecules have got a lone pair of electrons on the central atom. Whenever there's lone pairs on a central atom, this is a polar molecule. Carbon dioxide is perfectly symmetric because it's bonded to oxygens on each side, and there are no lone pairs on the carbon. So it is nonpolar. And therefore, which of the following would be the least ideal? Okay, the least ideal would be sulfur dioxide. Because first of all, it's an asymmetric gas, so therefore it's a polar molecule, and polar molecules have got higher IMFs than carbon dioxide, which is nonpolar. So when we say that ideal gases do not attract to one another, sulfur dioxide does not follow that approximation as good as carbon dioxide. So sulfur dioxide, when we use the ideal gas law, the numbers that we get from it will be very different from what the real life variable is. Carbon dioxide will follow it much better. Also, the molar mass of sulfur dioxide is greater than carbon dioxide. Since it has more mass, it also has more electrons, which means it also has got more intermolecular forces because of size. And also because it's bigger, okay, it's going to take up more volume. So that approximation of a gas not taking up as much space is worse with sulfur dioxide because as a bigger compound, it's going to take up more room. So they could ask you what 2 reasons explain why sulfur dioxide does not follow the ideal gas law as well as carbon dioxide. It's bigger, so it takes up more room than it should, and it's polar, so it has more IMFs than carbon dioxide. All right, that's Unit 3. We've covered now concepts in enthalpy, thermal chemistry, and calculating enthalpy, heats of reactions, and also gas and gas laws. So after watching this lecture, you now have the ability to finish your homework problems and also to go ahead and do the quiz. Then next week, we'll do some reviews leading into the test where we'll have a multiple choice and an FRQ exam on enthalpy, thermal chemistry, and gas laws.